Good morning, ladies and gentlemen. This is a third lecture on experimental methods and measurements on engine and vehicle emissions here at the Faculty of Mechanical Engineering at the Czech Technical University in Prague. Last time we have talked about what are vehicle emissions, why do we care about them, why they are important, and today we will talk about the basics of the measurement. For the students that are online, I ask to read the chat. I will put it also on the board here, that you should read the chat and write questions in the chat. For those that are not with us this fine January morning, you can call or email with further questions. So, start your engines, let's mash it on down, go for a ride. Here we go. Measurement techniques. Just to review, there are two types of emissions: greenhouse gases, which are chemically stable compounds that absorb in infrared region and contribute to the global climatic changes. They are not particularly harmful to human health. These are carbon dioxide originating from fossil fuel combustion, and from transport the two other relevant ones are methane from unburned methane from methane-based fuels, and nitrous oxide N2O, which is primarily produced in certain types of catalytic converter under certain conditions. The main reason why we were concerned about emissions in general are the emissions of reactive compounds that are hazardous to human health. They are generally short-lived in the atmosphere, so with the exception of black carbon, which is a strong absorber of light, they are not overly relevant for climate, but they are very relevant to human health. They are particles, both primary particles emitted by the engines and secondary particles emitted from precursors emitted into the air. That's called secondary aerosol. Then we have nitrogen oxides that originate from atmospheric nitrogen and oxygen under high temperatures and pressures in the combustion chamber, and tropospheric or ground level ozone, to which nitrogen oxides are one of the three necessary ingredients. The other two are organic gases and sunlight. And organic gases and sunlight we can have in the nature, but most of nitrogen oxides are of anthropogenic origin. Now, need to find some chalk that's longer than an inch, so I can, longer than 2.54 centimeters for those of you who insist on SI units. Some pollutants are no longer a problem, like carbon monoxide, benzene, lead, sulfur. Lead and sulfur we don't add in a fuel or remove them from the fuel. But we have new and emerging problems, and those are nitrogen dioxide produced in certain types of oxidation catalysts, ammonia which is formed during reduction of nitrogen oxides, aldehydes associated with the combustion of oxygenated fuels, and who knows what the future will bring. We need to measure the emissions during engine research and development when we consider new engine designs, new technologies, new fuels, new types of exhaust after treatment to know what are their effects or emissions. Are they bringing the reduction that we hope for? Do they contribute to the formation of some other undesirable compounds? That's all research and development tests. Then we have type approval tests to ensure that a vehicle that we would like to sell in Europe or United States or India or elsewhere in the world, that meets some emission standards. And because some manufacturers are satisfied with the vehicle meeting the emission standards in a laboratory, and who cares about what happens in the real world, then the type approval legislation are expanding to the whole vehicle life and also to realistic driving conditions where we get real driving emissions. So now we are expanding to the whole vehicle useful life and to realistic operating conditions. So that's to ensure adequate design and calibration of the engines, including exhaust after treatment. Then we have so-called aftermarket issues like tampering with the engines, tuning them to higher horsepower, removing particle filters, or at least not maintaining the engines properly. If you don't maintain the engine, well, there might be some problems. And particle emissions are one of the best diagnoses of the combustion process of the engine. Many problems with the combustion process or with the engine you see on emissions, especially particle emissions, way before you see them on drivability or fuel consumption. So many defects, failures, excessive wear are demonstrated by excess emissions. And vehicles with excess emissions are contributing very heavily, despite it's a small fraction of vehicles. It contributes very heavily to total vehicle emissions. And that's why we have programs to identify high-emitting vehicles with the intent to have these vehicles repaired or removed from service. And there we go for low-cost tests, just to say, okay, not okay. So for research and development and for the tests for type approval, generally we test either the engine or the whole vehicle in the laboratory. I will just write in a chat here that the lecture is streamed online from 266. So, for light-duty vehicles, motorcycles, automobiles, light vans, until some vehicle weight, in Europe it's 3.5 tons, that's metric tons, you test the whole vehicle. For heavier vehicles, you just test the engine, because heavy vehicles are not manufactured in large series. There is a big variety among vehicles, but there is not as many different types of engines. So only the engine is subjected to a test, and you see it here on the photo on the lab. We have the engine. This is Iveco 6.5 liter 6-cylinder turbocharged engine, fairly favorite for city buses, about 180 kilowatts, coupled with by a shaft with a dynamometer. This is a 4-quadrant dynamometer, meaning it can turn either direction and it can both absorb power and provide the power to the engine. And it's an asynchronous dynamometer, which means it's a synchronous electric motor coupled with a frequency converter, and that is coupled with the electric distribution grid to which we supply some engine power. The chassis dynamometer, the one in Rostocky, and there will be a lab tour in Rostocky, a virtual one tomorrow. I will also write it in a chat. Lab tour is online tomorrow, starting at 9 o'clock. This is a 4-wheel chassis dynamometer. Each wheel is coupled to a separate dynamometer. Not always you get such a complicated system. Typically it could be one axle which is connected to one dynamometer, and it's just a 2-wheel dynamometer then. What do we do with the exhaust? How do we measure emissions? Well, the total emissions are a product of the flow and the concentration of the given compound in the vehicle exhaust. And both the flow and the composition of the exhaust varies. So one approach is to determine emissions in each second of measurement, determine the flow, determine the composition of the exhaust, synchronize the two data streams, and then integrate it over the time. There are other approaches that we, for example, keep the flow constant. How do we keep the flow constant? We add variable amount of dilution air into the flow so that the sum of exhaust and dilution air are kept constant, and then we take out one of those two variables. So one approach is to dilute the exhaust for this purpose. You might want to consider diluting the exhaust for other purposes. One of them is you get water from the combustion. If you burn gasoline or diesel fuel, the concentration of water in the exhaust is comparable to the concentration of carbon dioxide, which could be 14% at stoichiometric air-fuel ratio, or several percent up to 10% about, plus or minus, on diesel engines. If you have an engine that's running on natural gas, methane, CH4, has twice as many atoms of hydrogen per atom of carbon, so the concentration of water is double the concentration of CO2, and it could be about 20% by volume in the exhaust. The exhaust is hot, so the water stays in the vapor phase. But as soon as you cool down that exhaust, the water starts condensing. If you look outside on a cold day with relatively high humidity, you can see white vapor coming from vehicle tailpipes. And that's not necessarily smoke. Most likely that's the condensed combustion water, especially on gasoline engines. You don't see that much with diesels because they have less water in the exhaust. So when you cool the exhaust, water may condense, and not just water. Many of the organic compounds that are in the exhaust can condense, and you get additional particulate matter formed from the condensation. And that makes for very difficult and not repeatable at all measurement. So the two approaches are either you do your analysis in raw exhaust. Big advantage of that is you don't further reduce the concentration of the compounds that you are trying to measure. So your effective detection limit is lower than if you dilute the exhaust. The disadvantage is you have to do all your measurements at high temperature to avoid condensation of water and organics. The other approach is to dilute the exhaust. You reduce the concentration, so you need instruments with lower detection limit, but you don't have to worry about water. You avoid condensation by diluting below the dew point of the exhaust. The mass emission rate is the product of concentration and the flow. So how do we measure both? Either if we measure raw exhaust, which we extract directly from the tailpipe, then we also need to measure the flow. We either can measure it directly or we can calculate it from some other surrogate values like the fuel consumption or the flow of air into the engine. It's technically very challenging, but it makes for a nice and compact installation. The other approach is to dilute the exhaust. You either dilute the raw exhaust, that's called partial flow dilution. You take sample of the exhaust, you dilute it, then you feed it to the instruments. Still you need to account for variable flow. Or you dilute all of the exhaust. That's called a full flow dilution. And you can dilute it in a tunnel in which you maintain constant flow. So you take away the variability of the flow. The flow is constant, so you multiply constant flow by concentrations that you measure. No synchronization of data is necessary. It's technically proven. It's used for legislative purposes, but the installation is rather bulky. You can see on this slide the scheme of the dilution tunnel. That's the DT. You maintain the flow in a dilution tunnel through some pump. And either you can have positive displacement pump, like a roots blower, that you vary the rotational speed of the pump, and by that way you vary the flow, and you measure the flow by either laminar flow element or some other measurement device. That's one approach. The other approach is you put critical orifice, or an orifice on which you maintain a critical flow. That means independently of the conditions in here, you get constant mass flow. Then you need a fairly powerful blower, because you generally need fairly high under pressure to maintain critical flow. So you have a constant flow maintained through the tunnel, and there is a slight under pressure in here into which all of the exhaust produced by the engine that's being tested is sucked in, plus variable amount of air that you feed through filters. And today, typically, you have a coarse filter which removes coarse particulates. You have an active charcoal filter, activated carbon, which removes most of the organic material. Then you have a HEPA filter, which removes very fine particles at very high efficiency. So, by the way, that's the perfect filtration mechanism. That's better than any face mask or respirator you typically use for coronavirus protection, because it's nearly an absolute filter. So you have variable amount of the dilution air and vehicle exhaust. The sum is constant. And from this flow, you take samples to gas analyzers and also for bag sampling. The gas analyzers can either measure online as you go, second by second, or you can sample the exhaust into bags. Those are Tedlar or Teflon bags, and sample is taken into them, and at the end of the test you extract portion of the bag for analysis, and you get one number per test, but it's a very accurate number. If you for example you find that you need to use different measuring range of the instrument, recalibrate the instrument, use a different instrument, you can still do that and analyze it again. You don't need to rerun the test. The advantage of online measurement is that you know in which portion of the test you have high or low emissions, and you can target your engineering efforts that way. In a similar way, we analyze particles. You can measure concentrations online, and you can also sample particles onto a filter for gravimetric analysis of total particulate mass. This is how the system looks in reality. This is from Horiba. It's my favorite manufacturer of emission measurement systems because the systems are very reliable. You get a chassis dynamometer, and then you have different tunnels for gasoline and for diesel. So you get exhaust through a insulated or sometimes heated transfer line, dilution air. There is a dilution air refinement system which supplies filtered air, and then you have a tunnel, and from the tunnel you collect samples on a filter, you collect sample into bags, and you direct sample to an analyzers doing online measurements. Not always you can do that. If you want to know, for example, emissions of a locomotive, there is no room to install a full flow dilution tunnel, so you need to extract a sample from the exhaust through a heated sample line, run it through analyzers, and then determine the exhaust flow. This is an example of real driving emission measurements. So, how do we go about measurements of basic pollutants? Okay, I read on the chat the camera is facing upwards. The lecture is streamed. Okay. Measurements of basic gaseous pollutants. What are the basic gaseous pollutants? And in the next section we will get into particulate matter emissions, carbon dioxide for the determination of fuel consumption and CO2 emissions, carbon monoxide, which is a regulated toxic compound, total organic gases or total hydrocarbons measured with a flame ionization detector, nitrogen oxides, which are measured as total NOx with chemiluminescence detector, oxygen, particulate mass, and particle number. You will see very soon in a legislation, and this is already in some heavy-duty vehicle legislation, ammonia can be measured with tunable diode laser or with FTIR analyzer, and nitric oxide, N2O, currently, tunable diode laser is in consideration, and I believe that measurement will be also possible with FTIR or possibly other infrared spectroscopy. For inspection and maintenance programs, we use a single non-dispersive infrared analyzer to measure hydrocarbons, CO and CO2, electrochemical cells for nitric oxide, NO, and oxygen measurement, opacity meter as a surrogate of total particulate mass, and there are new instruments and methodologies being developed for particle number emission measurements. Now, we will go through these analyzers one at a time. We will start with non-dispersive infrared. With non-dispersive infrared analyzer, you have some source of infrared light. This can be either a diode, it could be a laser, it could be a laser at fixed wavelength or a wavelength that you can tune, or it could be a broadband source like a heated ceramic element of silicon carbide, for example. Then the light goes through an optical cell. And it is detected by a detector. And either here or here you have a filter. So we have a source, we have the optical cell, we have a filter, the filter filters out all the other wavelengths and only allows specific wavelength of interest to pass through. That's called a band pass filter. Then we have detector. Each compound tends to absorb light in specific wavelength. That's a property of a molecule. It depends on the temperature, and we have a sample flowing through the cell, and a molecule here absorbs light, so this doesn't go. Then another molecule absorbs light. Now, what happens if there is a molecule here? Well, it's undetected because this light is already being absorbed. So just from looking at it, we have some non-linear mathematics behind this. What is measured is transmittance. T is, and that's a ratio of the intensity of the light transmitted over intensity of the light with no measured gas in its path. That's called I0. And if you plot transmittance as a function of the concentration of a given gas, then, or if we plot the intensity of the light, and this is the intensity at zero concentration, then this starts declining. And this is exponential relationship. And that's described in Lambert-Baer's law. To make these calculations easier, absorbance is defined as log negative decadic logarithm of transmittance. That means if nothing is absorbed, if transmittance is 100%, that means 1, then the absorbance is 0. If 90% are absorbed, then absorbance is 1. If 99% are absorbed, then the absorbance is 2. You can see that this measurement gives you maybe 1 or 2 orders of magnitude of useful range. As the concentrations get very high, well, you are very close to the noise level here. If the concentrations are very low, for example, you do measurement here, then what you measure, the difference here, is very small difference of 2 very large numbers. So there is also some detection limit in a low concentration, and in between here you have useful range of measurement. According to Lambert-Baer law, the intensity is the intensity at 0 concentration times e to the minus, and you have some absorption coefficient times the density of the gas times the optical length of the optical cell. So the optical length is a function of the instrument. You use it in the instrument design. If you want your instrument to be more sensitive, you increase the optical length. The absorbance is a function of it's a property of the molecule itself. It's almost a physical constant. And rho is the gas density, which is dependent on the temperature and pressure in the sample cell. In reality, the instrument manufacturer selects the proper length of the optical cell as well as all the other parameters like the strength of the source, the sensitivity and the range of the detector, and also the wavelength at which you are trying to measure. I will later show you some infrared spectra from which we will see that not all the compounds can be measured by infrared spectroscopy. You can measure the compounds for which you find absorption regions like carbon monoxide and carbon dioxide, where what you are trying to measure is absorbing nicely in some range of wavelength, and at the same time no other compound is absorbing. If you have multiple compounds absorbing at the same wavelength, you have to resolve which one is contributing to the measurement. So you have to measure at multiple wavelengths or measure it at high resolution. Most of the mid-infrared spectra is dominated by absorption spectra of water. This is this light blue, and carbon dioxide, which is here. And also there is a very nice absorption peak here, which doesn't show because it was simply too much absorption for this instrument. So you are in fact quite limited by what you can measure. So NDIR measurement is typically restricted to CO2 in here, 2500 reciprocal centimeters, which is about 4 micrometers, and possibly around here, 12-13 micrometers. You can also measure carbon monoxide and total hydrocarbons. However, each hydrocarbon absorbs differently, so it is an approximate measurement. It is not readily possible to measure nitric oxide or nitrogen dioxide, because nitric oxide and nitrogen dioxide absorb in the regions where you get a lot of absorption from water. Same thing for ammonia. So for the other pollutants, you need to find different method of measurement. For hydrocarbons, the favorite method and the reference method for most measurement is flame ionization detector. The flame ionization detector works on a principle that as you burn hydrocarbons, ions are created as the hydrocarbon molecule fragments during the combustion process. So in a flame ionization detector, you have hydrogen and air supplied, and you have a hydrogen flame. To that flame, you also bring sample of the exhaust that you are trying to measure. As the sample comes in and ions are created by the combustion of organic compounds or hydrocarbons, ions are created. So you put 2 electrodes, you apply some electric potential on them, and the ions are attracted to one or the other electrode. With the current, if you can talk about current, because it's individual elemental charges, very small currents. So you can measure very small currents that are produced by the ions, and the current is proportional to the concentration of carbon atoms in the sample. In actual instrument, this is more complicated. You get a fuel, you get a combustion air, you get some sample. You also have calibration gas, where you introduce gas with known concentration into the instrument for the purposes of calibration. We'll talk more about calibration a little later. You need to filter it, reduce the pressure, and control the flow. And all this is coming to the flame. 2 electrodes, enclosed chamber, and the signal is coming out. Flame ionization detector is very linear. There is zero response at zero concentration, and the response is proportional to the carbon atom concentrations. Now, oxygen atoms, if you have them in a sample, they tend to decrease the response. So if you are measuring oxygenated compounds like formaldehyde, for example, with a flame ionization detector, you get lower measurement. Nitrogen oxides, which cannot be easily measured in infrared spectra, they can be measured in ultraviolet spectra, but the technology of ultraviolet sources is still evolving. Nitrogen oxides are typically measured with chemiluminescence detector. Chemiluminescence detector is based on the reaction of nitric oxide with ozone, which produces nitrogen dioxide, and some of the nitrogen dioxide molecules are in excited state. And when they transition from the excited state to the base state, they emit photon of a very specific wavelength. So if this reaction is happening in the dark and you have the detector, it's a very selective detection of nitric oxide, because only nitric oxide produces nitrogen dioxide in excited state, which emits the photon that you detect. To make this quantitative, you supply lots of ozone, so this reaction is limited by nitric oxide coming with a sample. So you produce ozone from oxygen in an ozonator, a high voltage decomposition of oxygen. So you have oxygen from which you produce ozone, and then you have sample containing nitric oxide. Now, what happens if you want to measure other compounds of nitrogen? So if you want to do that, you decompose nitrogen dioxide into NO and oxygen. This you can do on a heated catalytic converter. I believe it's platinum, for example. So you convert NO2 into NO, then you measure the concentration of NO through chemiluminescence detector. So either you can measure NO or you can measure total nitrogen oxides. There are other types of catalytic converter that convert all reactive nitrogen species, including ammonia and NO2 into NO. And in that case, you measure, it's referred to as NOOY. And NOY is typically NO, NO2, ammonia, and possibly other reactive compounds. If you want to only measure NO2, you do it as a difference of total NOx measurement and nitric oxide measurement. Oxygen sensors. Historically, paramagnetic sensors were used. Now, many oxygen analyzers are solid-state zirconia cells like you have them in vehicles, and also tunable diode lasers are used for oxygen measurement, which is technology in development. The traditional paramagnetic detectors, they use paramagnetic properties of oxygen, which are temperature dependent. Oxygen can be magnetic under certain temperatures, and you measure the magnetic field created by the oxygen through fairly sensitive instrument. We will not ask you for details of the measurement. It's fairly complicated. How oxygen is measured in a car with an oxygen sensor. There is a zirconia-based sensor where small voltage is being produced if there is difference in oxygen concentrations on both sides. That response is rather steep, meaning as it measures either you have or do not have oxygen in the exhaust gas, because you get a very steep response, something like this, which is enough to maintain stoichiometric air-fuel ratio, because if you depart to lean or rich, you get large changes in voltage. That's a step. That's a step change for typical oxygen sensor. There are oxygen sensors that are able to measure a wide range of air-fuel ratios, and they work on a principle that essentially you have two cells. You have oxygen sensor facing reference air and a reference chamber at which you try to maintain stoichiometric air-fuel ratio lambda 1, and whether you have it or not, you can see from this oxygen sensor. And to maintain stoichiometric air-fuel ratio, you pump oxygen across this second fuel cell, and you pump it by supplying electric current. And depending on how much current you need to supply, that's called a pump current, to maintain stoichiometric air-fuel ratio here, from this you calculate the actual air-fuel ratio. So you pump current to maintain lambda 1 in the monitoring chamber, and you monitor that by the oxygen sensor. And from the pump current, you infer the air-fuel ratio. That's the basics of the measurement of gases. I will touch on a few things about instrument response. Let's say that you introduce some step change in concentration from here to here at some time 0. And this is some instrument signal, concentration reported by the instrument. So for some time, nothing happens. That's called the transport delay. And that could be the time the sample is traveling to the instrument, or the time the electronics take to react. Then you start seeing some change, and typically the response is similar to Newton's Cooling law, which means this is an exponential curve which asymptotically approaches the actual concentration. T90 is referred to as the time that %90 of the change is being reported by the instrument from the time that you start to see any response. Sometimes you determine this time where you measure 10%, and that's why it's called T10. So you can have times T10 to T90, also T90 to T10 when you decrease the concentration, or simply also T90, which is from 0 to 90%. Sometimes T90 response time is including the delay, but typically it should be that. This beginning, this onset could be approximated as linear only in this very beginning, and then this time, which is little over 60%, if you interpolate, this is little over 60% of the concentration that's measured. This time here from T0 is the time constant of the measurement. So T90 is then typically about 2.3 times the time constant. Especially with optical analyzers or any analyzers that are sampling into some volume, as the volume is being scavenged, the new sample is replacing the old sample, and if you design an analyzer, if you increase the flow, you increase the scavenging rate and you decrease the response time. However, if you increase the flow too much, then you get turbulent mixing here, and if you get turbulent mixing, then you increase the response because you never get the old sample out. It's just like I want to dilute my coffee, so I drink half of the coffee, I pour water in. I drink another half of the coffee, then I pour water in. At that point, I still have quarter of the cup is the original coffee, and 3/4 of the cup are water. Calibration of the analyzers. Every instrument should be calibrated. If you have a digital micrometer, you calibrate 0 level, and each instrument, if there is a nonlinear response, typically the software of the instrument adjusts it and it reports something. So ideally, when you measure 0, the instrument shows 0, and when you measure, let's say, 1, the instrument should measure 1. And the response is linear. In reality, you can have a drift. I will exaggerate here. Typically, it's very small, but drift is when something got added into the measurement. It could be either positive or negative. Then you can have an error in slope where the response is linear, but you always measure, for example, half of what you should be measuring. And third type is non-linearity, where instead of your response being linear, it's something like this, for example. So at the maximum range it's okay, but instead of being linear, it follows some curve. I'm exaggerating here. So it needs to be, every measurement device needs to be calibrated. Ideally, if you want that measurement to be conclusive, it needs to have metrological traceability to some primary standards. The primary standards are typically maintained by national or international metrological laboratories, and these primary standards are used to calibrate instruments that are used to prepare secondary standards, and these are used to prepare tertiary standards. And then at some point you get hold of, for example, calibration gas that you use to calibrate the analyzer. And that calibration gas is a gas mixture which has some declared concentration. Now, there is the nominal value of calibration gas. For example, you want 1000 ppm of carbon monoxide. In reality, you get, instead of 1000, you get, for example, 985. But the laboratory that prepared it guarantees that it's 985. Very seldom you can prepare it exactly. So there is preparation tolerance, but what concerns you the most is the certification accuracy. The better the certification accuracy, the more expensive is the calibration gas, but also the more accurate is your calibration. So you need to consider how accurate your measurement needs to be. And if it is a very accurate measurement and lots of money depend on it, then you should use high precision instruments, and also calibration gases with high certification accuracy. Typically, instrument calibration is, if you have instrument with 100% measurement range, then you do zero calibration. That's easy to do. You supply it with dry nitrogen or synthetic air. Synthetic air is a mixture of nitrogen and oxygen. And then you pick where you will be measuring. Typically at 80% of the range, you choose a concentration, and at that you do span calibration. So if the measurement range is, for example, 0 to 1000 ppm, then at about 800 or 900 ppm, you do span calibration. If the instrument has multiple ranges, well, sometimes it's good to do span calibration for each and every range. You do these daily before, and sometimes before measurement and after the measurement, to make sure that the calibration of the instruments didn't change. Periodically, you also verify the linearity. You put a span gas and zero gas into what's called gas divider, which prepares mixtures of span gas and zero gas at defined concentrations, and you do what's called linearity check or linearization of the analyzer to check for the linearity of the response. Then we have accessories. Samples going to gas analyzers typically need to be filtered. There need to be sample pumps, there need to be control of the pressure of the flows, and some handling of water content. Either the whole sampling train is kept at a high temperature through heated sample lines, or water is removed by cooling of the exhaust or the Okay, so that's emission measurement and gaseous emission measurement. I will do a short break. I will answer questions on Teams that are in the chat, and in couple minutes we will return to emission measurements, and we will talk about particulate matter measurements and advanced measurements.